Okay. Okay, great. So welcome everybody to another one of our IR SIG webinars. We've had a little bit of a hiatus, but off and get going with having a number of these webinars coming up in the next few months. So we're excited for you to join us today. My name is Meredith McGregor. I am an assistant professor at the University of Colorado Boulder and one of the new co-chairs of our IR SIG Leadership Council, along with Mike Zemkoff. So today we are going to have a webinar presented by Dr. Sarah Nickerson. Sarah just recently finished her PhD at the University of in Switzerland. And she is now working with Dr. Naseem Rangwala at NASA Ames and the Bay Area Environmental Research Institute. She's interested in developing computational methods of processing observational spectra on large scales. And Sarah will be talking today about a molecular inventory of the Orion hot core in mid-infrared with SOFIAEXES. And I forgot to mention, there are a few instructions for the webinar today. I put these into the Zoom window, so you can refer to them throughout the talk. In general, if you have questions for the speaker or any technical issues, please submit those through the group chat window. And then at the end of the webinar, I will unmute people who have submitted questions, let them ask their question directly to the speaker. You can also submit questions to any of us on the SIG Leadership Council so that we can discuss, deal with those at the end of the hour. And lastly, it's important to note that this webinar is recorded and posted later on our website, which is also linked through the chat window. And with that, I think, Sarah, take it away.
Thank you very much. Good morning, everyone, or good afternoon or evening, depending on where you are. Thank you very much for joining me in these interesting times. So today I'm going to talk to you about some recent research and results we've had of taking a molecular inventory of the Orion hot core using the EXES instrument aboard the SOFIA Observatory. And at NASA Ames, I've been working very closely with my supervisor, Naseem Rangwala. And I would also like to thank my colleagues who have also been contributing a lot: Curtis, Sean, Tim, Xintruan, Eric, Kinsuk, and Lou. And I also, would like to thank the IRSIG for this invitation today. And so just to start with, what are hot cores? So hot cores are the warm, dense regions near young, high-mass protostars. If it's a lower mass protostar, it's also known as a hot corona. So there's similar phenomena happening whether the star is high mass or lower mass. And so what happens is before star formation, there is the molecular cloud that's very cold and icy. And here the chemistry is frozen in and difficult to access. However, as soon as the star forms, it begins to awaken the chemistry. It heats up the ice, and then gas phase chemistry begins. And this is where it's a lot easier to observe everything happening in this very chemically rich environment. And here we find a lot of prebiotic molecules that will eventually become important for life. And in these hot cores, these systems, also the chemistry here is the building blocks for planetary systems and our own solar system. And so by studying hot cores, we can really begin to understand where the chemistry of our own Earth came from. However, looking at these hot cores with high spectral resolution and being able to view the individual transitions of each molecule, usually this has been done in other wavelengths, submillimeter, far infrared. But in the mid-infrared, however, there's several transitions that only happen here, and then also molecules without a perm dipole moment. We can only really see them in the mid-infrared. And so without mid-infrared, we're missing a huge piece of the puzzle here, what's happening in hot cores. However, the mid-infrared can be difficult to observe because from the Earth, because of all the interference from the Earth's atmosphere. And so this has been an understudied part of hot cores. And so just here showing the hot core I will be focusing on, this image in the center of the Orion hot core. And so you can see there's been a very explosive event here. There's about 3 radio sources in the center of Orion hot core believed to be protostars that probably their formation might have caused this
Hello.
event.
Hi.
Hey.
Hi, Mike. I'm okay. I was on another call. I'm watching another video. I just finished.
Okay, anyways, so the Orion hot core that I'm focusing on is IRC2. And this is found in the Orion KL nebula. This is the closest massive star-forming region to us, and it's also the best studied because it's so close. So the Orion hot core I'm focusing on is IRC2, and this is in the Orion KL nebula, which is the best studied and closest star-forming region to us. So this hot core is the hot core after which all other hot cores are named. It was discovered by Ho et al. In 1979, finding peaks in ammonia emission. However, despite this hot core being the one that is the prototypical hot core, it is, despite this hot core being the hot core after which all hot cores are named, it is still atypical. So most hot cores are internally heated. It's the region of molecular chemistry surrounding the protostar. However, IRC2 seems to be externally heated, and so it's more of a cavity or a window looking into a obscured source. One of these possible sources would be radio source 1, which is very nearby. And radio source 1 doesn't have an infrared component, and IRC2 doesn't have a self-luminous component, and so they seem to be a good fit for each other. And the radio source I is probably heavily depth obscured, which is why we don't see it in the infrared. And so here on the right is a composite image in the mid-infrared of the Orion KL region. IRC2 is this upside down U shape here, peaking at 12 microns. And then radio source I is just located to one side of it. And so now looking at spectroscopy, previous spectroscopy measurements for IRC2, Van Dishoek et al. In 1998 did do a survey of Orion IRC2 and with the ISO, the space-based instrument ISO, and here by going into space, you can avoid the Earth's atmosphere, obviously. And so they did find a very rich array of different kinds of molecules. They found some water, they found molecular hydrogen, carbon monoxide, CO2. They found acetylene and HCN. Also, but with ISO, they could only see the signatures of these, but they couldn't actually study in detail the transitions of all these because they did not have the spectral resolution. And so also studying this was Booman et al. In 2003. And they could see the strongest transitions for acetylene, HCN, and CO2. And there they could estimate excitation temperatures of about 175 to 275 Kelvin for IRC2. But again, they're not looking at individual transitions, but looking at a bunch of lines from the strongest transition. And then with the TAXIS instrument, which was ground-based, they really could see individual transitions of these lines. And so here they see the transition of HCN and C2H2. And But the problem is that TEXES was ground-based, and so there's a lot of the mid-infrared they could not access because of the Earth's atmosphere. And here they could measure about -10 velocity, for, local standard of rest velocity for HCN and C2H2. And this compares to the ambient cloud velocity of about 9 kilometers per second. And so they could see that the molecules in IRC2 is moving in an opposite direction as the ambient cloud. And so now moving to our own research, using the EXES instrument aboard SOFIA. The EXES instrument is really the sister instrument to TEXES, in that it has high spectral resolution, and so it can resolve the individual spectra, but because it's aboard SOFIA, it can fly above most of the water vapor in the Earth's atmosphere. And also with SOFIA, unlike space telescopes, because SOFIA lands at the end of every observation period, they can also fix it up, change out instruments, improve instruments, have upgraded instruments. So it's a really good advantage. SOFIA's in a really unique place in the astronomical community. And so what we did is conduct an unbiased line survey at high resolution between about 7 and 25 microns of IRC2 to see what molecules we find, because this is really a unobserved region. And so in the lower left-hand corner here, showing a forecast map in 7.6 microns of the region IRC2. So IRC2 is this region here. And then in the turquoise is the center where we peak up. And then the orange box is the footprint of EXES on it. So this is the region in which we will be taking our spectral information, and radio source I is nearby here. And so showing some of our early results of the spectra, we see acetylene, like other observers have seen. And here our acetylene, the Gaussians are asymmetric. And so we are picking up on 2 different velocity components, a main one here, and then a secondary one here. We see water in emission with a single velocity component. And then we also see methane. And so observing methane requires some, a bit more planning, because normally methane is in the Earth's atmosphere. And so we had our first batch of observations in October. And then the methane lines were right on top. The methane from IRC2 was right on top of the methane absorption in Earth. And so we would not be able to observe it. However, we took observations in February, and then because of the Earth's motion relative to Orion, the methane got shifted enough, Doppler shifted enough away from the Earth's atmosphere that we could observe it. And so we found about 6 methane lines. And then also it's showing the double Gaussian that acetylene has. We see CS, possibly. Have to analyze CS more, also the double Gaussian. We see silicon oxide in emission. And then we also see HCN. Here, again, the absorption lines here seem to show the double Gaussian, and so that leads to this means 2 velocity components. We see SO2, there's a lot of SO2 lines, probably about 100 of them or more. And then we're also seeing HNC, which is the isomer of HCN. And so with SO2 and HNC, we don't see the double peaked Gaussian. And so we don't see the second velocity component, but the data in the spectral region is also a lot noisier. So we're not sure if it's because the second velocity component does not exist for these species, or if it's because the data is much more noisy. And so we've seen over 350 lines so far and counting. And we see at least these 8 species. There's some other species that we suspect is there, but requires more analysis. And then also maybe there's even species we haven't even thought about yet. So we're going through these lines one by one and identifying which species they belong to, and then we'll see which lines are left over and we'll have to think hard about. And so for the absorption lines, the main velocity component is about -7 kilometers per second, which is similar to what Lacey found with taxis. And the second velocity component is not very resolved, and so it's going to require further analysis before we can say anything definite about that one. And so just to show you briefly how we analyze this. And so we're using the HITRAN and GISA databases in order to identify the lines that we are interested in. And then also in future, we're going to also look at exomol, because there's a few species in exomol that are not present in these databases, such as silicon oxide. And so from this, we can get the quantum numbers associated with the transitions, and also the rest velocity of the transition, and which species the lines belong to. And then from there, we normalize both the baseline around the line of interest and the atmosphere. We normalize them both to 1, and then we divide out the atmosphere. And this step is of varying importance depending on which molecule we're looking at. For example, acetylene and HCN are in regions with a lot of atmospheric interference. And so a lot of the lines are next to atmosphere or almost on top of atmosphere. On the other hand, HNC is in a very clean region. So there's pretty much no atmospheric interference. And then we fit the lines to Gaussians to get information out of that and integrate under the Gaussian for the column density. And then we're going to, as long as these are linear, when we're looking at the energy of transition versus the column density, as long as this is a linear pattern for each species, we can assume thermodynamic equilibrium and fit to Boltzmann's equation. And so here, essentially, we're just taking a relationship between the transition energy and the column density of each transition and fitting this linear relationship. We can find the excitation temperature and the total column density of the species. And there appears to be a random green line on my thing. Can I erase that? Clear all drawings.
You should be able to.
Yes, the random green line is gone. I don't know where that came from. I was not touching my computer. Okay. So showing some of these transitions that I'm fitting to. This is for acetylene, the R17 line. And so here in blue is the flux, and then the total Gaussian fit is in green. And then the Gaussian for, why is this doing this?
I'm sure somebody is accidentally doing that, so just keep going.
Oh, other people can draw.
I think so. So just
that's dangerous.
Delete them.
Okay. Anyway, so this is the acetylene transition, and so here you can see that there's 2 Gaussians for this line, so it's double peaked. The rest velocity is this straight line without any dots. Oh my God. Do we have another troll?
Yes, I'm sure we do. Just mic and hair on it.
Okay.
Start booting people out.
Oh my God. Okay. Okay, anyways, and so the dashed line is the main velocity component at about -7 kilometers per second. And then the dashed data line is the velocity component of the secondary line. So also going to HCN, we're seeing a similar story. The secondary velocity component is a bit less separated, a bit less resolved, but we also see it at about the same velocity. And the main velocity component has the same velocity. And going to HCN, I should note that these, the x-axis here is not all the same. But the main velocity component, the dashed line, is at about -7 kilometers per second. And so for HNC, we don't see the second velocity component here. Now going to the rotation diagrams here. So first looking at C2H2, so this is the ground state to V5 transition, and we're seeing these at around the 700 wave number range. And so at the moment, we're only analyzing the main velocity component of each Gaussian. And here we have a lot of lines. We see both ortho and para lines for P, Q, and R branch. And we are seeing different temperatures for each branch. So the P branch is colder at around 90 Kelvin, R branch 176 Kelvin, Q branch at 237 Kelvin. And so each branch is tracing a different temperature of the gas. P branch and R branch have about the same density, whereas the Q branch is a bit less dense. And so even though we're looking at the same line of sight, same position, we can see more than one component of the gas here. But they're all kinematically similar, so they all have some very similar velocities. So now we also see another transition, ground state to V1 plus V5, around the 1300s wave number. Unfortunately for these ones, for the para P branch, we only see 3 transitions because the other ones were right on top of atmospheric lines, unfortunately, but we get a very complete ortho P branch. And so they look a bit different. We're not sure how much to trust the para P branch, actually. But look at the ortho P branch. It is about 121 Kelvin, so similar temperatures to the P branch for the other transition, but this is tracing a much denser gas. And now here, we also see a number of transitions for the next most abundant isotope. Oh, sorry, there's a typo in the title. It should be 13CCH2. These lines were a bit more noisy, a bit fainter, and so this rotation diagram, looking at the column, essentially the column density versus the energy of transition, is a bit more noisy, a bit less coherent than the other ones because of the noise. And again, we're seeing similar temperatures and similar densities. And then we also, this would give us a ratio of the isotopes of 0.17. And now looking at the isomers, HNC and HCN. So these 2 isomers are very important. They trace the densest and coldest gas. And at lower temperatures and in dark cores, they're without any star forming activity. It's found that their ratio is near unity. But with increasing temperature, the HNC tends to deplete. And this is a bit of a mystery. It's not currently explained by all the theory or chemical reactions. And so in the theoretical chemical networks at the moment, something is missing as to explain why we see HNC deplete and not HCN deplete with increasing temperature. And so when we measure all these lines, for the HNC, we get 3 nice transition branches, P, Q, and R. Whereas for HCN, we get just Q and R branch. We do see 2 P branch points, but I think 2 points are not enough to fit properly. And so we're seeing the HNC trace colder gas at around 80 Kelvin, whereas HCN traces hotter gas at 190 Kelvin. And so the HCN is about 100 times hotter than HNC. And also it's denser. And so there's about 60 times more HCN than HNC. The lines have similar velocities, and also when we look at the shape and the widths of the lines, they are similar. And so what we're finding so far is in line with current observations. So now, how to analyze all this information. So just knowing that we see another isotope of H13CN, but we only have 3 very noisy lines for this, so we're not sure how much to trust the rotation diagram from these lines. And now what to do with this isotope is, or not the isotope, sorry, these isomers, HCN and HNC. So we're working with modelers to try to use this as a chemical clock to age IRC2. Because again, they start at about unity when something is a dark core before star formation really turns on. And then the ratio increases, there's more HCN and less HNC as the star begins to age. And so using chemical and temperature models of hot cores, we could begin to maybe find how old is the gas, how long has the temperature, has the IRC2, the star that it's giving us a window into, how long has that been forming? And then also there's some research showing that HCN can probe the inflows of star-forming regions in radio as observed in the radio wavelengths. So we need to see, is this relevant for us? Because we are seeing the velocity of the gas traced by HCN go in 2 different directions. And yeah, our findings are also within what other people found. So Schilke et al. 1992 were able to map the ratio of HCN and HNC in the entire Orion KL nebula. And there they found that the highest of the ratio was in IRC2, which peaked at about 80, which is similar to the number we get, 60. And then it decreases into less dense and in the colder regions away from there. And also the Orion RC2 itself has very interesting morphology. There are shocks in this region. And we find a number of chemical species that are linked to shocks. So it'll be interesting once we explore sulfur dioxide and silicon oxide. And then also the region has some OH, water, and SiO masers. And so it'll be interesting to link our findings to these masers. And so this region is very rich, very complicated. And as we analyze our data further, we're going to link all these things together to try to come up with a cohesive picture of just what is going on in IRC2. And so just to conclude and summarize, we're using SOFIAEXES to build a molecular inventory for the Orion hot core in mid-infrared. And so we've identified over 300 lines, and we can say for sure there are 8 species, but there's at least 3 or 4 species also suspected that we're going to analyze more to be more sure about it. And then also we need to find which species we haven't even thought of yet. So there's a lot more to come. And so far where we could measure things, namely with acetylene and HCN, we find similar numbers, similar temperature and ratios and velocities to what other researchers have found in the MIR. And we're ongoing to try to see where our results fit in with models and theory and other findings. And then also in future, we want to have a comparison between different hot cores. There's a lot of data, rich data in the SOFIA archives. And so these hot cores form in different environments, have different features, and we want to see how this affects really the chemistry of hot cores, and how the chemistry can also give us clues to the state of the hot core, and then also to see why some hot cores maybe have more molecules, more prebiotic molecules than others, to link it back to our own Earth. And I would like to thank you very much for your attention, and if anyone has any questions, I would be happy to answer them. Thank you.
Great, thanks Sarah so much for your talk. Okay, so we will open this up to questions. I believe the settings have changed so that no one can unmute themselves now. So the way we will work this is through the raise hands feature of Zoom. So if you have a question you would like to ask our speaker, you can raise your hand, and then I will unmute you and you'll have your opportunity to ask your question of our speaker. If you can't find the raise hands button, you can also type your question into the chat window, and we can work it that way either. Okay. Give people a second to. Give people a chance to. Oh. Okay. Unmuted. Nope. Hold on. Nope.
All right. Can you hear me?
Yes, we can hear you.
All right. Here's Bernard Schultz. Thank you for the nice presentation. There's obviously a huge amount of data here that you have to go through. Are there particular species where you need to go across wavelengths from EXES to TEXES? So where you basically have to work or use the synergy between those two instruments?
I don't know offhand what is the wavelength coverage of TEXES, actually. I would imagine they're quite similar because they're both MIR instruments. So I'm not sure if there's wavelength regions that TEXES accesses that EXES doesn't access.
Okay, thanks. Yeah. No, I just wanted to I wanted to basically highlight there that you know, there is definitely, I mean, some wavelengths are already available from the ground, and so it is important to understand that. And there's also a database, I believe the same database as where the SOFIA data is now, that also hosts IRTF data. Where TEXES is installed. So, you know, there may be more than you think.
Yeah, it's something I'm definitely going to look at as I comb through the archives and see. Yeah, starting with SOFIA archives, but also looking at archives for other instruments is definitely a good thing to do.
Mm-hmm. Thank you.
Thank you.
So we have two questions who've come through the chat window. So the first is that I presume you can derive the column densities of individual molecules. Could you have time to look for the abundance ratios of those comparing to hydrogen?
Yes, that's something we plan to do, and find another good measurement of molecular hydrogen in the region with another instrument, and then compare that so that we'll have the abundance ratios for them. That's something we're going to do in the future.
Okay, and a second question from the chat window. Why not include isolated not crystalline SiO2 as well?
I'm not sure if I understand the question. We see what we see. I haven't yet analyzed the SIO, but I'm going to once I download the data from EXEMOL. So I don't know much about the SIO other than we see it at the moment, but I will find out more.
Okay. Other questions from the audience, either via raising hands or typing into the chat window? Questions for our speaker. You can ask questions of those of us on the IR-SIG Leadership Council as well. Let me give people a few more minutes. I should also add that we generally have had these webinars roughly once a month at least. Typically it has been on the first Tuesday of every month. They're always at 1 p.m. Eastern time, 10 a.m. Pacific. So we will have more of these coming up in the future. So look out in your email inbox for future announcements of more IR-SIG webinars. And we are always interested in recruiting new speakers. So if you yourself would like to give an IR-SIG webinar or you have suggestions for speakers, please contact any of us on the IR-SIG Leadership Council. We are always especially keen to invite suggestions for early career scientists of diverse backgrounds. Okay. Well, if there are no more questions, I think we can, maybe leave this open for a little bit. So feel free to stay on and ask further questions of Sarah or any of us in Leadership Council. But otherwise, thank you so much for joining us today and bearing with our slight issues with internet trolls. And we look forward to having you join us on future webinars. So thanks so much, everybody, for joining.